Hello. Wait, give me a moment. Okay. Hello, my name is Isaac, and this is the EcoBin, solar-powered and self-cleaning deodorizing trash bin using rainwater collection with AI and IoT system. So abstract. So global water scarcity continues to threaten both urban and rural communities, especially where clean infrastructure is limited. Uh, So I'm here to present a smart solar-powered rainwater collection system that captures rainfall before contamination and monitors its quality in real time. So this design features a time of flight distance sensor and a water level detection, and an analog turbidity sensor for clarity assessment, and a microcontroller that transmits data to the Firebase for mobile visualization. Uh, this whole thing is powered by a 5-volt solar panel and a 3.7-volt battery, ensuring off-grid operation. And experimental results, which we'll go after in a while, have confirmed pretty high accuracy in the measurements. Yeah. So introduction. So water scarcity is one of the main global challenges of the 21st century. And although the planet is covered largely by water, only 2.5% is freshwater. So most of it is locked away in glaciers and deep underground aquifers. So in many of the developing regions, like rural and agricultural communities, people struggle to access safe drinking water. And according to the World Health Organization, like over 2 billion individuals worldwide rely on these contaminated sources, which increases the risk of diseases such as cholera. So rainwater is naturally clean when it first falls, and it becomes quickly contaminated when it comes in contact with soil. So we're trying to capture this rainwater like before it falls down, so it's clean. So our project addresses a growing issue by creating a simple yet efficient way to capture and store clean rainwater before it becomes polluted. Yeah, by collecting rain directly from the sky, preventing it from touching the ground. Uh, it the system doesn't not only provides immediate benefits for families, but also promotes a sustainable lifestyle by conserving natural resources. And in the long run, this will approach and reduce dependence on expensive infrastructure and bottled water while helping mitigate the effects of global water scarcity. Uh, so the system design, when rain falls, the water is directed into a barrel through a cover opening that prevents debris from entering. Uh, the the rain barrel is black, so it minimizes like penetration and discouraging algae growth. And the turbidity sensor monitors the water clarity, while an ultrasonic sensor measures the water level to calculate the available volume inside a rain barrel. The sensor is managed by an ESP32 microcontroller, which records data and transmits it wirely to a Firebase database, where users can monitor the water quality and level. So, and through a device which ensures transparency and reliability. So, uh, yeah, so to keep the stored water oxygenated and free from stagnation, a 5-volt pump periodically injects air into the barrel. Both the monitoring system and the motor are powered by the solar panel and charges a small lithium battery, allowing the off-grid operation. And this makes this design particularly suitable for rural and remote regions where electricity and infrastructure are limited. All right, so challenges. So in order to build a project, a few challenges have been identified. So one is the motor efficiency. So we need to find a strong enough motor to pump air into the barrel to like make the bubbles so it doesn't like stagnate. And this does not take up much power, but if the motor is not strong enough, it cannot force air up the column of water and won't work. Um, but if it's also too strong, it's probably too expensive for because the project should cost minimal money, and it'll also drain our small battery over time. So I resolved this by making the base of the barrel wider, hence the water level will be shallower, meaning that even a weak motor could potentially force air through the water to the top. And this is because that water is heavy, and going down a water column 3 meters deep will double the force of gravity exerted on a person. And making the bucket wider means that it'll have a shorter height and could also maintain the same volume. So the motor would actually work, and it conserves cost and energy consumption. The second is climate limitations. Another challenge is the climate that we're currently testing in. So I live in Southern California where like it doesn't rain or fog much, so testing is pretty difficult. And because of our minimal rainfall, the bucket will almost always be empty because of lack of water. And I don't think this is an accurate representation of the project's vision. And this method could not be used in certain climates. I included a map where like it could be used, like mainly in South America and like Central Africa. Yeah. Uh, so one thing I can do to solve this is to like test somewhere where there's more rainfall. Like yeah, as I said, and observe low amount of rain could be a potential place where pressure could be tested and see its full potential. Uh, The last one is voltage compatibility. Another challenge is that the voltage incompatibility with some of the devices in the monitoring system. The main circuit board is a ESP32, which could communicate on 3-volt logic, but when measuring the distance, the sensors operate on 5 volts, which does not work reliably with 3 volts. And also the sensor only sends data as analog, so we also need to convert it to digital to communicate with the rest of the monitoring system. One solution is to divide the circuit board into similar logic groups, and between the two groups we put a 3 to 5 volt logic converter, which will boost the signal and also decrease the signal the other way to maintain system compatibility. Um, yeah, and solutions. So the proposed smart rainwater collection system is composed of 3 subsystems: the storage barrel, the monitoring unit, and the control unit, the power supply. Together, these components operate a self-sustaining platform that autonomously captures, analyzes, and preserves rainwater for later use. The water subsystem centers around the compact solar panel that charges a 3.7-volt lithium-ion battery. And during daylight hours, the solar energy is stored in the battery and used to power both sensors and aeration motor. And when solar is insufficient, the panel can directly, uh, it is sufficient, the panel can directly operate a 5-volt pump, conserving stored battery energy for nighttime monitoring. And the monitoring substation is also managed by an ESP32 microcontroller, which collects the reading from the multiple sensors, an ultrasonic distance sensor that measures the height, and a turbidity sensor that measures the water clarity and detects potential contamination. The data is gathered and wirelessly transmitted to Firebase real-time database where users can observe system status as shown at the picture at the edge. So all through a web interface. So overall, the system integrates renewable power, real-time monitoring, and smart design to deliver a reliable, low-maintenance solution for safe water collection and limited resource regions. So next slide. So these are some important lines of code which I would like to discuss. So of code 1, the CircuitPython program continuously measures stored water quantity and clarity using a VL5304CD time of flight sensor and an analog turbidity probe, and uploads the results to Firebase. And the sensor is initialized over I2C with a 50 millisecond timing budget and a 60 millisecond inter-measurement period to balance the responsiveness and power. The read distance centimeter function waits for data ready and reads the sensor distance in millimeters and converts to centimeters, and applies a small mounting offset and retries transient errors. The turbidity channel is sampled in the analog in ADC to voltage function and converts raw ADC to volts and read turbidity NTU and maps voltage to an NTU estimate using a placeholder linear calibration. Uh, Level and volume function transfers the top distance to the water height percent full and volume in liters using cylinder geometry. And networking uses Wi-Fi socket pool and Adafruit request. And Adafruit NTP provides a proper epic timestamp. And each loop controls a JSON upload and issues an HTTP patch to devices, merging updates over that node for real-time dashboard. And the fixed real interval S cadence provides a stable telemetry suited to the solar battery operation. And the second line of code, this short CircuitPython routine demonstrates how the ESP32 measures the turbidity sensor's analog output when the voltage divider is used for signal protection. The turbidity sensor normally operates on a 5-volt supply, but the ESP32 can only go up to 3.3 volts. And to safely scale, a resistor divider reduces the voltage to the 3 before it reaches the analog input in the pin A1. The code imports analog in from analog I/O, defines an ADC channel, and implements ADC to voltage to convert the raw 16-bit reading into real voltage based on the 3.3 volt reference. The client application is a Flutter app, and it reads live telemetry from the Firebase real-time database node published by the ESP32, and it streams a percent full of volume in liters and the turbidity NTU, and renders them a simple dashboard, and can raise in-app alerts when thresholds are exceeded in real time. So back here, same image. So experiments. So experiment 1 is to validate the distance accuracy for the Adafruit VL53L4CD in a barrel-like setup by comparing sensor readings against ruler at fixed heights. Accuracy measures at this level because volume and alerts depend on it. So we placed a mat target at a measured distance 10 to 80 centimeters from inside a dark barrel mockup and moving in non-uniform steps to emulate common field levels. For each reference position, the sensor collected a single steady reading for a data ready, and small known mounting offset around 0.6 centimeters was intentionally left uncorrected to reflect a real insulation tolerances. All tests were performed indoors to minimize ambient IR variation, and dependent variable was measured distance in centimeters, and the independent variable was the reference distance. We reported the reported error, the measured minus reference, plus the MAE, RMSE, and medium, like absolute value of error to characterize the central tendency and robustness to outliers. So figure number 1. So across 9 data points from 10 to 80 centimeters, the sensor tracked a reference line closely with the resistant positive bias from the uncorrected mounting offset. The near linear agreement indicates the sensor is stable across a tested range for water level estimation, and residual bias explains most of the error can be removed via one-time offset calibration, subtract 0.6 centimeters, or by measuring the exact sensor to lid standoff after installation. For capacity calculations, the 0.6 centimeter height error and a 90 centimeter barrel corresponds to a less than 1% error in percent full, which is acceptable for alerts. So I therefore conclude that a TLF sensor provides sufficiently accurate inputs for monitoring subsystem with straightforward improvements available through calibration and a median of n sample filtering. And experiment two, we emulated calibration by sampling the turbidity probe output across 9 standards: 0, 10, 20, 50, 100, 200, 400, 600, and 800 NTU. An analog output from 0 to 5 volts was passed through a resistor divider to an ESP32, and for each standard, a single reading was captured and converted to volts. And because many low-cost optical turbidity sensors are approximately linear over the 1 to 800 NTU region, we fit the least squares linear model, and we reported our regression coefficients and residuals to be a goodness to fit. And the resulting equation can be inverted into firmware to estimate the NTU directly from the voltage. This is experiment 2, figure number 2. I'm 6. Oh, sorry. So the measured voltage decreased as turbidity increased, which is consistent with reduced transmitted light. Uh, and our outcome is that both our sensors are very reliable on real-time monitoring of water level and quality. Other related work. So a study of urban stormwater management evaluated rain barrels as a method to reduce accelerated stormwater runoff, particularly from residential roofs. And this proposed strategy diverted only roof runoff into a 50-gallon barrel and connected to 25% of a 2,000 square feet roof, irrigating a 150 square feet garden, and results showed a 2.4 to 5% reduction in growing season runoff and a 1.4 to 3 annual percent decrease depending on irrigation practices. And although this system effectively reduces runoff and benefits small gardens, its impact is constrained by limited barrel capacity and geographic conditions. Compared to this approach, our project expands this concept by integrating sensor-based monitoring, solar-powered automation, and data reporting, enabling more efficient and scalable water conservation beyond seasonal use. Also, another study on the adoption of stormwater best management practices, or BMPS, example uh, examine factors and influence the long-term use of rain barrels across two urban and suburban watersheds in Indiana. Uh, Surveys, interviews, and field assessments revealed that participants with longer experimental values and higher awareness of conservation practices were likely to adopt and maintain BMPS. Gardeners aiming to reduce water use were also identified as the most common adopters, while 25 to 35% of installations were discontinued within 5 years. The study suggested that community engagement and educational signage could improve retention, and compared to this societal behavioral approach, I think our system enhances longevity by providing automated monitoring, remote tracking, maintenance alerts, and reduced reliance on sustained user motivation. So a conclusion. So while the smart rainwater collection system demonstrates a strong potential for sustainable water conservation, several limitations were observed in this development. The battery capacity reduced continuous operation of the aeration motor, especially during prolonged cloudy or rainy periods with limited solar input, and this could result in water stagnation and potential microbial growth. Expanding battery capacity or implementing power-saving logic, such as adaptive sampling intervals or motor duty cycling, could improve reliability without sacrificing autonomy. Another limitation is the system's dependence on Wi-Fi connectivity to transmit data to the Firebase. In rural regions with weak to no internet access, this would restrict real-time monitoring. Integrating cellular or satellite communication would enable global access and promote deployment, like almost everywhere. And a pre-filtration module could be added before the storage, like before the water goes into the barrel, to remove airborne contaminants, improving both safety and water quality. Thank you for your attention. Thank you.